the chapter called Magnetic Effect of Electric Current in a simple way so that it is easier to understand. First of all, we have to understand what is a magnetic effect of electric current. So whenever the electric current passes through any conductor, it produces a magnetic field around itself. So whenever a current is passing through any insulated copper wire or any of the conductor surround itself with a circular magnetic field. That zone is called as a magnetic field or magnetic effect of electric current. Whenever near that conductor, if you bring a magnetic compass needle, what happens that the magnetic compass needle deflects, showing that magnetic field is around the conductor. So this effect is called as magnetic effect of electric current. So whenever the question arises, what is a magnetic effect of electric current, you should know that whenever a current is flowing through any conductor, it produces a magnetic field around itself in the formation of a circular ring. So this effect itself is called as magnetic effect of electric current. On the basis of this effect, there are a lot of devices which are working nowadays. So next is when electric current flows through a wire, a magnetic field is produced around itself. So now this shows the relationship between electricity and magnetism. The relationship between electricity and magnetism, that magnet can create an electric field. So whenever, according to Faraday's law of electromagnetic induction, it states that whenever you keep a copper coil in between a magnetic field and make that coil to rotate in between a strong magnetic field, EMF is generated. So vice versa, electric current flowing through a conductor creates a magnetic field around itself, and the same thing, a magnetic field can produce electric current when we move a copper coil in between a strong magnetic field. So this is the thing how magnetic effect and electric currents are related to each other. Next, we will study that magnetic field and field lines. So magnetic field and field lines is that whenever you take a strong bar magnet, so for example, if you will take a strong bar magnet, the magnet has two poles. That is, one pole is called as north pole, especially it is indicated by red color of a bar magnet, and another pole is called as a south pole, which is represented by blue color. So that any magnet has two poles. When you tie it with a thread and suspend it, it will always align itself in the north south direction of the earth, pointing that earth is also one type of big magnet with its pole. So whenever you align a magnet freely suspended on the air, the magnet align itself in the direction of north and south direction of the earth. So same day, a magnet is surrounded by magnetic lines of force or magnetic field. So these lines of force actually starts from north pole and move towards the south pole. It starts from north pole and move towards the south pole. If you tell it as, it starts from north pole and terminate at the south pole outside the magnet. So outside the magnet, it is starting from north pole and terminating at the south pole. But inside the magnet, it is starting from the south pole and terminating at the north pole. So starting from north pole and terminating at south pole, and inside the magnet it is starting from south pole and terminating at north pole. And these magnetic lines of force are continuously surrounding the magnet, so above the magnet and below the magnet also. So these magnetic lines of force is called as magnetic flux, and these flux are surrounded by the magnet. Near the magnet or the near poles of the magnet, these magnetic fields of lines are very strong. But as we move away from the pole, the strength becomes lesser and lesser, and the quantity of magnetic field of lines also reduces. So these field of lines which are present in around the magnet are never intersect each other. So they are free from one another or one above the other. So these magnetic field of lines of force itself is called as magnetic flux. So this flux density is more near the poles because the strength of there are concentrated magnetic lines of force near the poles, showing that the strength is more near the poles. Next is okay. Next we will come as right hand thumb rule. So this right hand thumb rule states that whenever you hold any conductor with your right hand, so that the thumb represents the direction of the current, and all these forefinger surrounds the conductor like this. If you surround the conductor like this and thumb represents the direction of the conductor, then all the forefinger surrounding the conductor represents the magnetic field around the conductor. So this is the right hand thumb rule. So right hand thumb, whether you hold the conductor in this way or you can hold the conductor upside down. So this thumb represents the direction of the conductor flowing in the straight conductor, and these forefinger represents the magnetic field around the conductor. So this is called as right hand thumb rule. So in the simple example, this is called as right hand thumb rule. Whether you hold the conductor in this way or whether you hold the conductor in this way. So this is called as right hand thumb rule. So whenever the question comes, what is a right hand thumb rule? Then this is the right hand thumb rule. It states that whenever you hold a straight conductor in which current is flowing, already that conductor is connected to a circuit where through a DC supply or alternating current is flowing through that conductor, and when you mark it as holding that conductor in manner, it shows that the thumb represents the direction of current, all the forefinger represents the direction of magnetic field surrounding that conductor. Whether you hold upside down or like this, it shows the right hand thumb rule. Magnetic field due to circular loop. So we have now understood that whenever you catch hold of a straight conductor with your hand, the thumb represents the direction of the current, and all the other finger represents the direction of a magnetic field around the conductor. So if it is not a straight conductor, if it is a loop or a circular loop, at the time how the magnetic field surround itself. So if you take a circular loop around conductor and conduct the ends of that round conductor like a bangle, but it is not fully completed, half is cut, so that two ends of that circular loop is connected to a battery or a source of current. So that time when current flows through that circular loop, how the magnetic field is surrounding that loop. So if you do that with an experiment, that take a cardboard and make two holes on either side of the cardboard, make the conductor to go through that hole and form a circular loop, and fix it with the ends of that conductor are fixed to a what you tell source of a current. It may be a battery or any other source. So when you connect switch on it, the current starts to flow through that circular loop. At that time magnetic field is surrounded. So that can be detected using a compass, keeping over that cardboard, and see that deflection occurs near the circular loop, showing that a magnetic field is surrounded around that circular loop when the current is flowing through that. So this circular loop has magnetic field in such a way that the field on the two ends of the circular loop, circular field lines are created on the both the ends of the loop, means from where the current is circular form is there are continuous circular concentric circles near the two ends of the coil, and above the coil also there is a concentric circles. But at the center of the circle, means if this is a circle, at the center the magnetic field is not circular, but it is a straight line, showing that it is a straight line. So this shows that this is a in the middle of that circular loop, it is in the form of a straight line. On either side it is a circle concentric circles, but in the middle of the circular path it is a straight line. So this is called as a magnetic field surrounding a circular loop. Next we will study about magnetic field due to a solenoid. So what is solenoid? Solenoid is just if you take an insulated copper wire and surround it to any cylindrical cardboard, like for example, if you see a pipe, a cylindrical pipe, if you wound a insulated copper wire over it, copper coil it, and that insulated copper wire which will around a cylindrical pipe or any cardboard like agarbatti cardboard will be there. If you will surround insulated copper wire, that copper wire will act as a solenoid. So in that solenoid, if you connect that solenoid copper coil like this surrounded over a cylindrical cardboard or a cylindrical pipe, a water pipe, if you cut it in a small single length pipe and surround a insulated copper wire over it, this acts as a what do you tell it, as a solenoid. So this is called as solenoid. Means any coil which is surrounded over a cylindrical form. If you remove the pipe also, that cylindrical wire itself is called as a continuous wounding of a cylindrical coil. It may be 100 turns, 100, 200, 300, or maximum number of turns you can create. As you increase the number of turns, the magnetic field created by it also increases. So this is called a solenoid. So when you make that solenoid and connect the two ends of that coil to any EMF source, it may be battery or any other source, then a current starts to flow through that solenoid. So when current starts to flow through that solenoid, uh, magnetic field is created around the solenoid. Now that solenoid has two poles. As in the bar magnet there are north and south, in the same way the solenoid creates two poles where the current starts flowing from one end and it starts to flow to the other end. The starting point is creating a north pole and the end point is creating a south pole. So it creates same as the bar magnet. A magnetic field means starting from one loop and ending at other loop. So there are continuous a magnetic field around the solenoid. So on which factor these magnetic field depends? It depends upon number of turns of that coil. How many number of turns? It is this principle is used in electromagnet. So if the number of turns increases of that solenoid, the magnetic field also increases. The strength of that magnetic field also increases. So the number of lines also force also increases. Flux density also increases if you increase the current. It also depends on the quantity of current flowing through that circuit and the voltage applied. If voltage is more and current flowing through the conductor is more, the concentric circles of magnetic field also increases, and it depends on the number of turns of that coil. So if coil number of turns increases, then the magnetic field around it also increases. This principle are used in creating electromagnets. Wherever we will create electromagnets, we will use this principle. We will wound a maximum number of turns of insulated copper wire over any iron bar or wherever we have to create a electromagnet. So maximum number of turns, it may be 100, 500, 600,000 number of turns. How much quantity of strength we need, that much number of turns of copper coil is made around any magnetic property of that metal. We will use that type of metal. It may be iron or any metal which can be converted into electromagnet. So there this principle is used. Next we will learn about, so electromagnet I told we can make electromagnets. So electromagnets are used in different purposes in, for example, in alternating motor. So AC motor, we will create a electromagnet there. In electric bell, electromagnets are there. In speaker, electromagnets are there. In your mobile phone also electromagnets are present. In different antennas also there is a requirement of electromagnets. In speakers it is used, and in vehicles it is used, in dynamo it is used. There is a lot of requirement of electromagnets, where we will use copper coil wounded over a magnetic property which can hold magnetic, converted into magnetic thing. That type of metal we will use and wound a copper coil and make a stronger magnet. Next we will learn about electric motor. So on the principle of this, we have generated a electric motor. It is based upon Fleming's left hand rule. So electric motor, there are two types of motor, whether it may be alternating current motor or direct current motor. Direct current motor or DC motor is a motor which we can run through direct current.
अभी ये क्या कर रखा है आपने, पूरा घर बंद करके? दोपहर का नहीं खाया ना? ठीक है। दाल बना रखा है मैंने, बाद में आते टाइम थोड़ा सा गर्म चावल चटनी बना रखा है।
So electric motors we were talking about. There are two types of electric motors. So one is called as DC motor and another is called as AC motor. The DC motor runs over direct current, the source which produces direct current, for example, a battery or any DC source. Though that type of motor which runs over direct current is called as DC motors, and whichever the motors which run over alternating current, alternating source is called as AC motor. So these motors run over the principle of called Fleming's left hand rule. Fleming's left hand rule states that whenever you will align all the three fingers of your left hand, that is thumb, forefinger and middle finger, at right angles to each other, then the thumb represents the direction of motion of that conductor, the middle finger represents the direction of the current applied to the conductor, and the forefinger represents the magnetic field. So if you align all the three fingers of your left hand like this, so here the middle finger represents the direction of input current, and the forefinger represents the direction of magnetic field. Then the thumb represents the direction of the motion of the conductor. So this principle is called as Fleming's left hand rule, and this rule is used in motor rule, or it is also called as Fleming's left hand rule. So this left hand rule is used in both alternating current and direct current motors. So this principle is called as motor rule or Fleming's left hand rule. So in DC motor, what is there? There is a rotor over which a number of coil insulated copper wire coils turns are made, and it is kept in between a strong magnetic field. The ends of the coil are connected to a commutator where commutator are connected to split rings made up of copper rings, and it is called as split ring. These split ring are connected to carbon brushes which are sliding on the both of the split ring. The carbon brushes are connected to the external circuit to a source of a DC source. That DC source may be a battery or any other DC source. When we switch on, the current flows through the battery towards the carbon brushes and then to a split ring, and through the split ring the current flows to the coil. So when the current flows to the coil, it is kept in between a magnetic field. So when the current flows through the coil which is kept in between a magnetic field, the torque is obtained by the rotor. So the principle is that whenever a current flowing conductor is made to made to present in between a strong magnetic field, a torque is obtained by that coil. So this on this principle, the coil starts to rotate or in between a strong magnetic field. So on this principle, the motor is made on the basis of the rule of Fleming's left hand rule. In the same way, in AC motor, what we will do, instead of using a split ring, we will use a slip ring. So wherever we are using a slip ring, it is called as AC motor. Wherever we use a split ring, it is called as DC motor. In a slip ring, is there, and the ends of the rotor there are two and when the current is made to flow, alternating current is made to flow through these slip rings, the current flows through the coil which is kept in between a magnetic field, and strong torque is obtained and that rotor starts to rotate. So this type of motor, which is consisting of a slip ring, is called as alternating motor, and which consists of a split ring is called as direct current motor or DC motor. So next we will study about dynamo. So there are two types of dynamo. One is DC dynamo, another is AC dynamo. DC dynamo are the dynamos which can produce direct current. AC dynamo are the dynamo which can produce alternating current. DC dynamo are the dynamo which can be made by putting split ring in the commutator part, and AC dynamo can be made by making a slip ring in the commutator part. So here vice versa. In motor, what we used to do, in motor we used to give the current to the copper coil which is kept in between a magnetic field. Here what we will do, we will convert a mechanical motion of that rotor which is kept in a magnetic field to produce electric current. In dynamo we are using a vice versa, that we are making the coil which is kept in between a magnetic field to take a motion, and whenever the copper coil kept in between a magnetic field move, then EMF is generated in the coil. The flux linking the coil changes and EMF is generated in the coil. So this principle over which we will make the coil to rotate in between a magnetic field and produce EMF, this is called as a dynamo. So this works on the principle of Fleming's right hand rule. And Fleming's right hand rule, if you align all the three fingers of your right hand in such a way they are right angles to each other, then your middle finger, your forefinger and thumb, so the thumb represents like this. If you align, the thumb represents the direction of motion of the conductor which is kept in between a magnetic field, and forefinger represents the direction of magnetic field, and the middle finger represents the direction of EMF generated which is taken out from that coil. So this principle is called as dynamo rule. So dynamo rule is Fleming's right hand rule, and Fleming's left hand rule is your motor rule. Next, on what basis the EMF generated depend? The EMF generated in the coil depends on several factors. First is strength of a magnetic field in between which that coil is kept. Next, the number of turns of the coil which is kept in between a magnetic field. So on this factor, and the strength of the magnet. So on all these factors, the EMF generated in the coil depends. If you increase the number of turns of the coil, EMF generation also increases. If you increase the strength of the magnet of that which is kept on the either side of that core, that also EMF increases in that coil. Also, it depends upon the distance of the magnet kept from that coil. So if the magnet is kept very near to that coil, EMF generation increases. If it is kept far away from the coil, EMF will reduce because strength of the field also reduce. So it also depends upon nature of the core over which that coil is wounded. The core means the rotor over which that coil is wounded, and number of turns of that coil. Daily application of this, we will use this principle of wounding a copper coil and making it an electromagnet is electric bell, loudspeaker, electric motor, magnetic relays, and magnetic cranes. They're all we will use an electromagnet, and also these electric motors and dynamos are used in certain vehicles wherever it is used. So next we will study about the force on a current carrying conductor in a magnetic field. So this is the same principle we will check in a motor rule. So whenever you will keep a conductor, straight conductor in between a magnetic field and make a current flow through that straight conductor, a torque is obtained to that conductor. Torque means a push is obtained to that conductor. That push itself is called as a torque. So this is obtained because whenever a current carrying conductor is kept in between a magnetic field, there is a torque obtained. So this torque itself is called a push, and on this principle motor is made, whether it is AC motor or DC motor. So this force on a carrying conductor kept in between a magnetic field. So maximum we have finished this chapter. So we will revise something. So we understood the magnetic effect of electric current, that whenever current carrying conductor or straight carrying conductor, magnetic field is a circular magnetic field is surrounding that conductor. Next, that can be done through activity. Take a cardboard, make a pinhole over it, and make the straight conductor to pass through it. And if we apply current through a DC source, so current starts to flow through that conductor, and the concentric circle magnetic field is surrounded that conductor. You can check it with a magnetic compass needle. When you bring that compass needle near the conductor, the compass needle deflects, showing that concentric circles of magnetic field is surrounding that conductor. conductor. Next, if you take a bar magnet and keep it over a cardboard and put some iron filings over it and shake it, so these iron filings surround itself, forming a magnetic field around itself, showing that magnetic flux is present around the bar magnet. It starts from north pole and terminate at south pole. The concentration of iron filings is more near the poles, showing that magnetic field strength is more near the poles, and these iron filings are less near the um, uh, above the magnet, showing that the concentration of magnetic field is less. So magnetic field lines of force starts from north pole and terminate at south pole. Magnetic field due to current carrying conductor. When current flows through any conductor, a magnetic field is surrounded by the conductor. That can be done by that same experiment. You take a cardboard, make a pinhole, and make the conductor to connect to a source. When current passes through it, concentric circles of magnetic field is surrounded by the conductor. Magnetic field in a loop, a circular loop is made with a insulated copper wire and is connected to a source from where electric current passes. Concentric circles are made near the two ends of the loop, and in the middle of the loop the magnetic fields become like a straight line, showing that the concentric circle reduces and strength reduces at the center of the loop. Next, magnetic field in a current in a solenoid. That same solenoid I told, if you make a insulated copper wire to surround any cylindrical cardboard or cylindrical pipe, the concentric circles of insulated copper wire made, and the ends of the coil are connected to the source of a battery. Then what happens when you allow the current to flow through that solenoid? It behaves like a magnet having two poles, north and south pole. The lines of force starts from north pole and terminate at the south pole. So the strength of the field is more near the poles of the solenoid, that is north pole and south pole. It's same behaves like a bar magnet. So this principle is used to make electromagnets, and the strength depends upon number of turns of the coil. It may be 100, 200. As you increase the number of turns from 100 to 100,000 or may more, the strength of the magnet also, electromagnet also increases. It also depends upon the core of a material or a metal which is used. So on these all factors the magnetic strength also depends. Next is force on a current carrying conductor in a magnetic field. So if you keep a conductor and make the conductor ends of the conductor to connect to a source of a battery, and which is kept in between a magnetic field, what happens? The current, when current flows through that conductor, turg is obtained, a push is obtained by the conductor, and that push is called a turg. So this is the effect which is called as force on a current carrying conductor which is in a magnetic field. So this is used in a Fleming's left hand rule. This principle of turg is used in Fleming's left hand rule, or it is also called as motor rule, where we will make a core or a copper coil which is kept in between a magnetic field. So whenever you pass through a current through that conductor, there is a torque obtained, and this torque is used as a mechanical energy. This principle we will use to make DC motor and AC motor by converting electric current into mechanical energy. Wherever there is a mechanical in motor, in every wherever the motor is used, everywhere we will use the convert the electricity into mechanical energy. In electric trains we will use this motor. In mixer grinder we will use motor. In crane we will use motor, and many other devices. In your floor mill we will use motors. In industries we will use motors. So there may be DC motors also, there may be AC motors. So all these work over the principle of Fleming's left hand rule or motor rule. That is, whenever copper coil kept in between a magnetic field, a current flows through it, a torque is obtained. So this torque shows that that whenever current flows through the conductor, which is kept in between a magnetic field, what happens? A torque is obtained. Next we will see that electric motor. So electric motor is that whenever copper coil, so there are two types of motor. One is DC motor, another is AC motor. DC motor, it consists of a split ring in the part of a commutator, and AC motor, it consists of a slip ring in a commutator part. But in DC motor we will provide the source, which is a direct current power source, which flows through the split ring and to the coils, which is kept in between a magnetic field. When current flows through this, a torque is obtained by the coil, and that coil starts to rotate in between a magnetic field. This is called as DC motor. Vice versa, if you keep it in a slip ring, if the ends of the commutator is slip ring and current flows through it, alternating current flows through it, the torque is obtained by the coil, and the coil or rotor starts to rotate. This is called as AC motor. So this works on the principle of Fleming's left hand rule. It states that whenever you align all the three fingers of your left hand, that is forefinger, middle finger and thumb, in right angles to each other, then the for middle finger represents the input of current. You are putting the current from the source, that is input of current, and forefinger represents the direction of magnetic field. Then thumb represents the direction of motion of that conductor, which is kept in between a magnetic field. So motor rule, Fleming's left hand rule. Electromagnetic induction. Electromagnetic states that whenever a copper coil which is kept in between a magnetic field is made to rotate mechanically, EMF is generated in the coil. So the EMF generated in the coil depends upon number of turns of the coil which is rotating in between a magnetic field, the strength of the magnet in between which this copper coil is kept. On all this principle, the EMF generated in the coil depends. So Faraday's law of electromagnetic state that EMF generated in the coil, whenever it is kept in between a magnetic field and made to rotate, EMF is generated in the coil. This EMF generated in the coil depends upon several factors: number of turns of the coil and the magnetic field strength in between which the coil is kept. Then we will go for Fleming's right hand rule. Fleming right hand rule is also called dynamo rule. In dynamo, it is a vice versa, where you will take that Fleming's right hand rule. Right hand rule states that when you align the all three fingers of your right hand at right angles to each other, the thumb represents the direction of motion, forefinger represents the direction of magnetic field, and middle finger represents the direction of electric current produced or induced in the conductor. So this thumb rotation of the core in between a magnetic field in dynamo, it is rotating like this. The thumb represents the direction of motion. Mechanically it is made to rotate with any external source like turbine. We will use it in hydraulic power station or a wind turbine. It is made to rotate with the external source like wind or waterfall. So the turbine rotates, the rotor rotates. Thumb represents the motion of that rotor in between the magnetic field. The forefinger represents the direction of your magnetic field, and the middle finger represents the production of electricity which is induced when the rotor rotates in between a magnetic field. So this is Fleming's right hand rule, or it is also called as a dynamo rule. Next is domestic electric circuits. So domestic electric circuits are the circuits or which is used in domestic wiring. So there are different types of wiring. One is used as called as a domestic wiring, which is used in house wiring, and another is called as industrial wiring. In 10th class field, 10th class, it is told as domestic electric circuits. So domestic electric circuit consists of a pole or a electric pole through which electricity is coming for power station or electric board. So it the current from the wires are made to come towards the domestic zone through the electric poles. These electric poles consist of two wires. One is called as a live and another is called as neutral, and another one is called as earthing. The three live wires are coming. One is live wire, another is neutral, third is earthing. So these connections are made to come to the building where wiring has to be done. So it these wires where live and neutral are connected to the meter, through which the electric current is made to move further in the domestic circuits inside the house wiring. So through the meter the connection is made, and through the meter the wire, the live is connected to the four connections. So two are connected to the input and two are taken out from the meter. So live and neutral are connected to the meter point. There are four connections like this. Two are input to the meter and two are output from the meter. The two wires from the pole are made to come and given to the input of the meter, and two wires from the meter are taken out from other two terminals points of the meter. So these two wires run, and all the circuits, house wiring inside the wire, inside the house are connected in parallel to this live and neutral. And wherever the earthing is made outside the house by putting a copper wire deep inside the earth, and we will use earthing materials such as charcoal, salt, or wherever we have copper coil and all those things. We will make it in a deep underground and may bring out a wire which is called as earthing wire. So we will use it for earthing purpose in order to give a safety to all devices. If any short circuit happens, excessive current flows to the earthing, so protecting your device and electric shocks. So for that purpose we will make earthing outside the house, so that we have a earthing wire. So mainly live wire is made as red or yellow, and neutral wire is made as a color code is made as black, and your earthing wire is made as a green or any other color we can use it. So three wires we will use it, and all the connection which are made inside the house are in a parallel connection, not in a series connection, in parallel. So whether it is you are connecting a bulb or a fan or electric device, all are connected in parallel circuits. Your switchboard, your uh, point of connection where 3 pin electric connection is made, there are three terminals. One is live, another is neutral, and another is earthing. Three connections are made. If you see the switchboard, there are 3 points. So one is live, another is neutral, upper one is your earthing. So these are switchboards, and your electric bulb is connected with 2 points. One is phase, another is neutral, phase or live or neutral. So always the switch is connected to the phase, not neutral, because when you switch off, no current flows to the electric board. This protects the electric short. You should not never connect the switch to neutral. Always connect the switch to make on off switch to the live wire. So once you switch off, electric current flowing through the circuit stops, totally stops, and prevents electric shocks and current flowing through the circuit. If by mistake if you connect it to a neutral wire, then current starts to flow through the circuit. There is a continuous flow to the current to the device. If any other short circuit happens, the device may go faulty. So it is necessity to connect the switch to the live wire. Go to any other chapters and some question answers over this chapter in next class. Thank you very much.